In this video, I want to show you how to make this wormhole sphere in Unity with C# code. So this is really an icosahedron, but it's a sphere-like object with a bunch of different wormhole exits in it. And from the outside, it kind of looks like a virus. So it's strange, and if you'd like to learn how to make it, stick with me. Okay, we'll start with a new project. It's going to be a 3D project, and I'll call it Wormhole Sphere. And that's going to take a second to create, so I'm going to pop over to the terminal and cd into the directory that it creates pretty quickly. And I'm going to cd down into the assets directory of that and clone my repo into the scripts folder. And then I'm going to cd up into the root of the folder, the project directory, and open VS Code just to check to make sure that my scripts are there. And they do appear to be here. So I'm going to pop back over to Unity. And I'm going to start by deleting the main camera and the directional light. We don't need those. I'll go ahead and create an empty object and call it mesh. And I'll create another empty object and call that mesh maker. To the mesh, I'm going to add two components, the mesh renderer and the mesh filter. And then in the assets folder, I'm going to create another folder. I'll call it materials. And right now it's just going to contain one material, so right click, create material, call it mesh material. And I'm going to go ahead and change the color because I prefer blue. And then I'm going to go to my package manager, and I'm going to go ahead and import an asset that I've already downloaded from the asset store. It's a double-sided shader. I have this in my other video as well, and I show more about how to download it, but if you just download that double-sided shader you see that I'm importing, it should work for you. And then I'm just going to go back to my material, and I'm going to pick that shader. Okay, so now on my meshmaker object, I want to add two scripts, the mesh drawer and the mesh maker. And on the mesh drawer, I'm going to pull over the mesh onto the mesh filter and mesh renderer. And then I'm going to generate my mesh. And apparently I forgot to add the material to the mesh. So I'll go to the mesh and I'll expand the materials drop down and go grab my material and drag it in there. And there we go. So this is it. It doesn't have a light. It's kind of dark in here, so I'll get a point light in there. And I'm just going to expand the range so that it reaches the sides of the sphere better. Okay, and then that is my wormhole sphere. So we'll go back to the mesh maker here and play with some of these parameters. Check the auto update box, so it's auto updating. That's changing the length of the wormholes. This is going to change the size of the icosahedron or the sphere. And then you can also change the number of sides that the polygons have. So here I'm changing the number of sides that the polygons have that form the cylinders that form the wormholes. And you can clear the mesh and then generate it. So that's it. Okay, so let me give you a brief rundown of how I did this. So I started with this icosahedron, which is a kind of spherical-esque shape made of 20 equilateral triangles on the faces. But instead of these equilateral triangles, what I'm going to do is replace it with what I call a wormhole triangle, which is really just the triangle with a wormhole in the middle of it. Now, the hardest part about these wormhole triangles, let me reduce the cross section to just a square, or I can reduce it to just a hexagon. But the point is, I can change the number of sides on this, and as the sides go up, it becomes more and more circular. But whatever the number of sides is, I've got to cut a polygonal hole in this thing as a function of the number of sides. And so kind of how do you do that in general? And if you look it up online, you'll find things about polygonal clipping. Those are more complicated algorithms for more general polygons. right here, we're just dealing with like origin-centered regular polygons. And in fact, since I'm doing half number of sides here, we're just dealing with polygons with an even number of sides. I've reduced the problem to that. And so I found a simpler way to do that. What I do is I kind of box out the polygon. So I'll add these little strips that turn the polygon into a rectangle, and then all I have to do is draw a rectangular hole inside of an equilateral triangle, and that's going to be really easy to do. So I just solve it in two different steps. I draw a what I call a polybox border around the polygon to turn it into a rectangle, and then I draw the rest of the equilateral triangle with a rectangular hole in it. So just to be completely clear, here's an equilateral triangle with a rectangular hole in it. The red here is the rectangular hole. You can see I've divided it into 7 different triangles. One is right here, and then there's 3 quadrilaterals, each with 2 triangles in it. I'm not sure if I drew, the slash from the top left to the bottom right, or the top right to the bottom left, and similarly for these, but it really doesn't matter. Point is, I divide the equilateral triangle into 7 different triangles with a rectangular hole in the center. And I can repeat that for any rectangular hole as long as it fits neatly within the equilateral triangle. Okay, just to show you a little bit of the code of how the polygon box borders form. So this is all boilerplate code up here. This function here is really where the magic happens, this build mesh data function. So basically it gets the bounding rectangle. So let's look at what this looks like in code. So the bounding rectangle would be like this point, that point, that point, that point. And then it loops through all of the vertices of the polygon, and it gets, that vertex and then the next vertex after it. And it's basically going to draw a triangle between the original vertex, the next vertex, and the corner of the bounding rectangle that they're closest to. And I call that the quad, the quad that they're in. So there's one corner of the rectangle per quad, and we're going to find out what quad these two guys are in, and then draw a rectangle between them, a triangle between them and that corner of that quad. Okay, now this is the only kind of potentially confusing logic here. So I find the quads of each of the vertices, and I say, okay, if they're in the same quad, definitely draw a triangle between them. But also, if they're in different quads, but the quad of the second one is ambiguous. So let me give you an example of that. So here there are no ambiguous quads. So I'm going to change to a different one. Here there are ambiguous quads because this point, that point, that point, and that point are all ambiguous. Let's take this point, for instance. This one could belong to quad 1 or quad 2. It's right in the middle of both of them. So I say in this case where the second, and this is only the second one is ambiguous. So if the first one's in a quad and then the second one is in a different quad, but it's ambiguous, right on the corner, go ahead and draw a triangle. And you're going to draw the triangle between to the corner of quad 1, whichever one quad 1 points to. So right here, this triangle would be formed. And then on the other side, this one's the first one. This is the next vertex. Well, there's no ambiguity there, and it would just draw the normal triangle between these guys. And then this next one, okay, this is the original. This is the next one. There is ambiguity, so we're going to draw a triangle in the quad of the first one. So it would be this triangle here. So that's all this logic is doing. And it works for even regular polygons. So like I was saying here, and I take it back, there are ambiguous vertexes right here and right there, but there aren't any on the top here. So to show you an example of a triangle that wouldn't be drawn, so we definitely, if this was the first one, this was the second one, we draw the triangle there. But then if this is the first one and this is the second one, we do not draw a triangle there because these guys are in separate quads, and this guy's quad is not ambiguous in this case. Okay, so just wanted to explain that code. That's the only potentially confusing part, but that ends up kind of, you can see, filling out the triangles of the border one vertex at a time, and it just loops over all the vertices. So if there's 6 vertices in this hexagon, then it's going to try to draw 6 triangles, and in this case it only ends up drawing 4 triangles. Now I want to talk about how I rotate these wormhole triangles and push them out to form the faces of the icosahedron. So I form each of these wormhole triangles in this specific configuration, and they're centered at the origin. And then I'm going to rotate them and push them out onto the faces of the icosahedron. So let's pop into how I'm doing that. And while we're looking at this code, I want to show you with a kind of demo. And this is a square, but it could, it could be a square, a triangle, whatever. This same logic's going to work with any type of polygon we're talking about. The rotation is going to be done in 2 different stages. So say this is my starting triangle, and just arbitrarily I want it to fill in a face that's oriented like this. So obviously it's different, and so the first rotation I'm going to align the normals. Now it still might not be aligned, because let's say that the ending rotation is kind of rotated a little bit around the normal too, so that the points, the edges, line up correctly with all the triangles, or squares in this case, but triangles around it. So so that's 2 different rotations. So first there's the rotation to align the normals, and then there's a second rotation around the normal to align the edges, the vertices. Okay, so let's pop into this code here. So first it calculates the normal of the starting triangle and the ending triangle, and it calculates a rotation axis and a rotation angle for the first rotation to align, and so this defines the first rotation to align the normals. And you can see that the rotation axis I choose is the cross product of the start normal and end normal. So if this was your start normal, this is your end normal, you'd want to rotate around a third axis that is perpendicular to both of those. So you'd want to, and if you're not familiar with rotations, you might need to look up rotations a little bit, but the cross product of this vector and that vector gives me a vector pointing in that direction, and I can rotate around this vector onto the other vector by rotating around this axis that's perpendicular to them. And this axis that's perpendicular is given by the cross product of those two vectors. The cross product of 2 vectors is always going to be perpendicular to both of them, unless of course it's 0, which I'll talk about in a moment. And then the rotation angle, the amount that I need to rotate, is this a property of dot products. So if you're not familiar with dot products, you might want to go look them up. But basically, if I take 2 unit vectors in 2 different directions and I take the dot product of them, then that's going to give me cosine theta, where theta is the angle between them. And so if I do the inverse cosine of whatever is output by that dot product of these 2 normalized vectors, then that gives me the angle between the vectors. That tells me how much I need to rotate around that rotation axis to rotate the start normal onto the end normal. Okay, and then this quaternion is just something in Unity that helps it calculate these rotations really easily. And basically, this is nice because you can just pass in the rotation axis and the rotation angle, and it'll output a quaternion which completely describes your rotation. And then you can also pass that into this matrix 4x4.rotate function to get a rotation matrix. So you can apply that matrix to any of your vectors, and it'll output the rotated vector. Okay, and then here I'm just calculating the center of the ending triangle, and that's actually going to be how much I need to push out the rotated triangle onto the surface of the sphere at the very end. After I do both the rotations, then I'm going to push it out onto the surface of the sphere. And the reason I'm calculating it here before I even calculate the second rotation is because the second rotation is going to align the vertices. So say this is what I get after the first rotation, and this is what it's supposed to be. So I want this vector to be rotated onto this vector. And so that's essentially what I'm doing in this code here. I say grab the first vector from the starting triangle and the first corner of the starting triangle and the first corner of the ending triangle, and calculate the vector from the center of the triangle to that vertice or that vertex. And so you can see that I'm subtracting off the center from the ending triangle because I want the vector from the center of the triangle, wherever that may be, to the edge of the triangle. I'm not doing that for the first triangle, and the reason is because the first triangle is already centered at the origin, and rotating it a little bit won't change that either. Now you also say, well, this isn't rotated yet. That's what I'm doing here. So here I take that edge that describes, it's not an edge, it's a vector from the center of the triangle to the first edge, to the first vertex, and I rotate it. I apply the first rotation matrix to it. So I align the normals. And then I'm just trying to figure out how much I need to rotate it further to align, to make the corners end up in the right spots so that it combines to all of the triangles around it correctly. So I need to rotate it by the first rotation matrix to align the normals, and then I'm going to figure out, okay, now how do I rotate this partially rotated first vector onto the ending vector in order to align all the corners. And we use the same thing. We do a cross product again. But here, this one is a little more complicated, and it's I should have, in the arbitrary case, I would have had to do this with the first rotation too, but the first rotation just didn't happen to have any start and ending normals that were parallel or anti-parallel. But if the two vectors in a cross product are parallel or anti-parallel, the cross product is going to give you 0. And that's just a property of cross products. But if it's 0, in this case, it's going to give me basically a 0 vector. It's going to be an undefined rotation axis. And so my second rotation is not going to work. And I did run into that problem with this one. So I had to add this little bit of logic, basically saying, okay, if the second rotation axis is essentially 0, near 0, then set it equal to the end normal. And the reason I'm able to do that is, obviously, after the first rotation, the normals are aligned. Then I'm trying to rotate the, say this vector onto that vector. Well, obviously, that's a rotation around the end normal. And you might think, well, why can't I just use the end normal then? Why do I take the cross product at all? And that's because, well, it could also be around the negative end normal. And so the cross product is actually correct to handle that. But in the case where the cross product, doesn't come through, it gives you a 0 answer, it's okay to use the end normal. And I explain why that's okay to use the end normal there and not have to worry about like the sign, whether it's the end normal or the negative end normal. I kind of explain why here, because if they're parallel, there's no rotation to do. They're already parallel. If they're anti-parallel, then you're rotating it by 100 degrees. So anti-parallel would be, okay, this first vector is pointing this way, and it's supposed to be 180 degrees the opposite way. Well, it doesn't matter if I rotate by this vector or that vector, the normal or its negative. 180 degrees is going to put me in the same spot whether I'm rotating with the positive or negative. So it really doesn't matter in this specific case whether we should be rotating around the positive normal or the negative normal. And so that's why in this special case it's okay to set it to end normal, but it's not okay to do that in the general case, which is why you still need to use a cross product. And then it's the same thing. You just find the angle between the vectors and you rotate it around this second axis by that angle. And then down here I just combine the two rotations into one combination rotation matrix. And then so when I'm transforming the vectors, so I can pass in a list of vectors here and it just returns the transformed vector, and the way it does that is to first rotate it by the combined rotation. So it does both the first two rotations, and then it translates it out onto the surface of the sphere. So it's 1, 2, 3. So it's 2 rotations, and then a third step is the translation. You might also be thinking to yourself, well, he's explained, how to make the polygonal hole. He's explained how to rotate and translate these triangles, but he hadn't really explained how to make this complex looking wormhole structure. I do that in a separate video, so I'm going to link it in the description below and hopefully on the video at this timestamp. But refer to that video for how to generate this kind of wormhole structure in general. The only other part that we haven't talked about is kind of how to put it all together. So this is the function that I put it all together in. You'll see some calculations here, square root of 3, that comes from the geometry of the equilateral triangle, but I don't want to get into all that because that would be exceedingly boring. What I want to talk about here is the fact that I'm doing multi-threading, and I'm also creating a single wormhole triangle centered at the origin in the kind of default rotation or default orientation. And I'm going to clone this object and then rotate it and translate it into place on the surface of the sphere rather than remaking all of this, because this has to do with, how do you calculate kind of the splay and how the wormhole looks and all that. I just want to do that once and then just clone whatever the mesh I make there is. So that's what I do here. So for each of the triangles on the surface of the icosahedron, I start a new thread in which I clone that wormhole triangle centered at the origin in the default orientation, and then I transform it by doing those 2 rotations, so the rotating the normal, then rotating around the normal, and then translating it out to the surface of the sphere. And I just join back all of these 20 different threads that I create there, and then join together all the meshes into a single mesh that I render on the screen. I also wanted to point out that, I am using cloning and multi-threading here. I also have a branch in here, 3 different branches, all prefixed with timing. But this branch is kind of the brute force approach where there's no multi-threading, no cloning. I just recreate everything from scratch and I do it sequentially. There's another one where I use multi-threading, but I still recreate the wormhole every time. And then there's one that's like what you're looking at here, where I use both cloning and multi-threading. Surprisingly, the brute force approach was actually most of the time faster than the other 2. It ran in 30 milliseconds on my computer, so I guess that's just hard to beat. There is some overhead with creating, other threads and then joining them together. So I guess the overhead just made these other 2 approaches slower, but I was a little bit surprised that the brute force approach was faster. But I left this as the multi-threaded approach because, if you wanted to make this more complicated, it'd be better to do multi-threading, and it's just kind of better coding practice, and it's not that much slower, so I left it that way. The other thing that I wanted to point out here is the entry point to the code. So if you watch my other video, you kind of know the entry point, but I just wanted to point out that when you click this generate mesh button in Unity, you're calling this code here in this editor for MeshMaker. And when you click clear mesh, you're calling that code. If you have that update checkbox, auto update checkbox checked, then every time you change something in that editor, you'll call this this function here. And this part just draws the default editor. So it puts all of these parameters here where you can change them right there in the editor, and it gets those parameters from whatever the variables are defined in here. So, here's the auto update, and then you change the size of the sphere that's right here, and you can control the ranges and stuff. So I just wanted to point that out just in case you wanted to play with that. That's all for now. Thanks for watching.